Professor Bialis here. In this video we're going to talk about the last section in Chapter 7, Section 7. And in this section we are going to talk about how to simplify complex fractions. Now, first of all, what is a complex fraction? A complex fraction is not like a hard fraction. It's a fraction that has a fraction within it. Okay? So complex fractions are fractions that have fractions within them. What we're going to do is simplify that. We don't want to ever leave that as our final answer. We want to have just a regular fraction with a single denominator, a single numerator, single denominator, and that's it. Okay? So there are two methods that they talk about in this section. Both methods could be used all the time. Okay? However, I think one method lends itself to certain situations and then the other method to other situations. So I'm going to show you when those situations occur. So let's just jump right into some examples and see how this plays out. So again, this is section 7.7 and we are simplifying complex fractions. So first thing, let's look at this. Now, notice how I wrote this. When I wrote that, I made a very clear distinction between this fraction, these two fraction bars, and this one. If you write it like this, then it just kind of, melts together into one big ugly thing. So when you're writing this, make sure it's very clear where your overall numerator is and your overall denominator is. So as you can see, we have a fraction that has fractions within it. It's complex. Now, when we have a single fraction over a single fraction, this is what the book would call method 1. And what that's getting you to realize here is that fractions mean division. So when I have this over this, I'm going to rewrite this as 3a over 25b squared divided by 9a squared over 5b. Okay, so fraction over fraction is a fraction divided by a fraction. And once we get there, we're dividing fractions. There's no more complex fraction. So to multiply, remember, I multiply by the reciprocal. And we have that. And now I reduce and multiply, nothing new. So 3 and 9 are going to reduce by 3. A 5 and a 25 are going to reduce by 5. 1a is gone, 1a is left. 1b is gone, 1b is left. So I multiply across here, there's nothing left, it's just a 1. And then in the denominator I have 15ab. And now I have a normal fraction with a numerator, denominator, end of story. So really all this is dividing fractions. We just have to know that that's what we're doing. But once we know that, then there's really nothing new to this concept here. Okay? Let's look at one more like this. Okay, so same thing, we have a single fraction over a single fraction. When that happens, I am going to write it as a division problem instead. Okay, when I divide fractions, I'm actually going to multiply by the reciprocal. And now I just simplify and then actually carry out the multiplication and I'm done. 6 and 12 reduce and that's pretty much it. Okay, so these are close but they're not completely opposites. So factoring out a negative is not going to help me. What I'm left with is an x times x plus 5 and a 2 times x minus 5. If you want to distribute that out, by all means go ahead. Completely unnecessary though. I really wouldn't even bother. I would leave it as this. And there we go. Okay. Now this next one's going to be a little different. And you'll see what I mean in a second. Now, what's different about this is that we don't have a fraction over a fraction. We have multiple fractions over multiple fractions. Now, what we did in the first two examples was what the book calls method 1, where you take that bottom one, you invert and multiply, and you're done. What we could do here is get a common denominator, pull these together in a single fraction, same thing here, pull them together, and then go through method 1. You can do that. Or you can treat this almost like an equation. Now, what I mean by that is, in equations, we cleared fractions out. We were able to do that because what you do to one side, you do to the other. Okay? In this case, you can clear those small fractions out again because what you multiply on the top, you multiply on the bottom. Okay? So this is what the book calls method 2. And I personally prefer this method because it just seems a little cleaner in this situation. So we have 4 fractions within that one big fraction. Now I need to have an LCD that covers the entire thing. So I've got y's, I've got x's, and they both have a high exponent of 2. So I'm going to have x squared, y squared, all the way through. I reduce, and then we'll see what we're left with. Y squareds cancel out, so I have x cubed when I multiply those together. Y reduces, so I have x squared y. Don't lose that negative there. Here the x squareds reduce, so I have y cubed. And here the x's reduce out, so I've got minus xy squared. Okay, before we move on, there was a lot going on there. Just read through it again, make sure there were no silly mistakes. Then I continue through, and I have to try and reduce that rational expression now. It's no longer a complex fraction. It's just a normal rational expression. So I'm going to take out an x squared, x minus y. Here I'm going to take out a y squared, y minus x. Now, in this case, those two binomials are truly opposites of one another. So what I'm going to do to fix that is I'm going to take a negative out of the top, which will change those signs. Now those match and can be reduced out. So what I'm left with is that. And we're good to go. Okay, so method 1 was a fraction and a fraction, you turn it into a division problem. But when you have multiple fractions, what I prefer to do is that method 2, where you clear those fractions out. And again, it's the same basic idea as what we did with equations. It's just why we're allowed to do that is what you multiply top, you multiply on the bottom. Okay? Let's look at another one. Okay, now you might be looking at that and saying, well, where's the complex fraction? I don't see a complex fraction. It's not there yet. Okay, what you should notice are all those negative exponents. Now, negative exponents, remember, tell you to take the reciprocal within that term. Okay, now, that doesn't mean things on top go to the bottom. Okay, because these keep every term separate. We have a sum and we have a difference. So when we move top and bottom, we're looking at each of these terms as something separate. Okay, so this is how we're going to rewrite this. Anything with a negative exponent flips to the other side of that fraction. So I'm going to rewrite this as a 2 over x. X to the first, but I would just write an x. So I just bring that x down. Plus 3 over y. Over here, 1 over x. Here, 2 over y. Just the thing that that exponent was attached to moves down. Now I have a complex fraction. And this is just like the example we just did, where we're going to use that method 2 idea where we clear all those out. The LCD among the entire thing is xy. So I'm going to multiply all 4 of these terms by xy. The x's cancel. I have 2y. The y's cancel. I have 3x. The x's cancel. I have y. The y's cancel. I get the 2x. I always think, can that be reduced? Can that be factored and carried out? In this case, there's nothing to factor, nothing to reduce. That's the best we got. Okay? So again, the complex fraction idea, we're trying to get these small fractions out of there. That doesn't mean all fraction is gone, but now it's just a normal rational expression. Okay, let's look at one more. Okay, same basic idea, but I want you to pay attention to the difference between this and this. The negative exponent tells you to take that reciprocal, but it's only what it's attached to. Only the x was raised to the negative 1. Here, the entire 3x was raised to the negative 1. Okay, that's what I want you to get out of this example, is pay very close attention to what those exponents are attached to. And now, I'm going to clear those fractions out again. Now remember, not multiply these by x, these by 3x. It has to be the same thing throughout. So all 4 of these terms need to multiply by 3x. So I have 15x. These x's cancel, so minus 9. I then get 6x, and all of this goes away, so I have a plus 1. Okay? Now, always think, can I factor this? And in this case I can, by taking a 3 out, like so. Now, did that allow me to reduce anything? Unfortunately, no. Okay, still the best answer is everything laid out, factored out, like it is here. However, since that didn't allow for any reducing, this is an okay answer as well. So both of these would be acceptable. This is a little bit better because it's completely spelled out. Okay? So with complex fractions, you have those 2 methods. Both of those methods could technically be used at any problem that I would give you. Okay? The only problem that sometimes comes up with this method is if the LCD is just so huge you can't handle it. That doesn't happen very often. And I don't believe there's any problems that they would throw at you now where that would happen. But again, I would use both methods when they're appropriate. Okay, they can be used every time, but I would use that method 1 when it's just fraction over fraction, and then this method 2 when there's multiple fractions within there. Okay, so as always, work hard. Let me know if you have any questions, and I'll see you next time.